Okay, so first, thank you for your coming and for this first lecture on my mini course about stochastic geometry and statistical mechanics. So stochastic geometry is related to continuous object, like in the colloquium 2 days ago. So it's a word in general based on Poisson point process, and we build random geometrical object like the Boolean model in the previous talk. And in general, in this kind of random structure, we don't have any interaction between the object. It's classical in stochastic geometry. And in the part, statistical mechanics involves random spatial model with interactions. So it's clear now what is the topic. It's between stochastic geometry and statistical mechanics. And so it's about a random geometric model with interaction in the model. So this kind of model appears in biology, when the cellulars, in the tissue cellular, or in the foam, or in many other topics in science. So for this first lecture, I would like to talk about a real process. So it's quite old result. It's directly related to the Widom-Rawlinson model, so in the 70s. So it's quite an old result, but it's exactly in the topic of the mini course between stochastic geometry and statistical mechanics. So I would like to give you some precise results about this model to introduce this topic. Yeah. So, okay, so let me just recall the Boolean model I called 2 days ago. So we consider N a Poisson point process in Hardy, and for simplicity, I suppose the radius are not random today. So I fix a positive radius, and the Boolean model is just defined by the union of balls centered at the point of the Poisson point process. So it's just the union for the point in the Poisson point process of closed ball centered at X. So just recall quickly, we have the point, non-random radius, and the Boolean model is just the union of this ball. Okay, so it's a typical object in stochastic geometry. And now, what about interaction? We'll add interaction on this object. So for that, we need an interaction, and how to define interaction. The classical formalism is about Gibbs modification. So what does it mean? We consider an energy, and here the energy will be exactly the volume of this of the Boolean model, and the volume of the Boolean model will be the energy, and we have the Boltzmann-Gibbs formalism. So density with respect to the Poisson point process will be exponential minus beta times the energy. So just to define the energy is defined only in finite window, because if you have an infinite number of balls, it's not possible to define. So we consider lambda included in RD, so such that the Lebesgue measure of lambda is not equal to 0 and finite. And we consider so P lambda is the law of n lambda. So the Poisson point process in the window lambda, the law of the Poisson point process in the window lambda is denoted P of lambda, P lambda, okay? And so the the area process will be, so I fix beta in R, and what is the area process is just the following law. So it's exponential minus the energy, and the energy will be beta times, so the energy is the volume of this set here, and here we consider L omega. So L of omega is just this quantity here, it's here L of n if you want. So this is exponential minus the energy. So the point produce this set here, and we consider the volume of this set and times beta here. And of course, the reference measure is the Poisson process here. And of course, it's not a probability measure. We have to normalize it by a constant, which we call Z lambda, because it's a partition function in statistical mechanics. So this is the area process here, infinite window lambda. Okay, not in general in statistical mechanics, when beta is positive, it's called the inverse of temperature. And okay, so it's classical. And but we can define also it for beta negative, and it's a general model for the area process. Historically, this model was introduced by William Robinson because he has a nice property, and it was only at this time for beta positive. But so it's quite clear. So Z lambda is just the integral of this quantity here. And it's not really difficult to see this quantity here is bounded. It's bounded by the volume of lambda plus boundary condition. But this quantity is bounded, and so finally it's quite easy to prove this quantity is positive and finite. So this model is well defined here for any beta. Okay, so of course let me know if something is not clear. And okay, so just to answer why this exponential form, why do we use this exponential form for the density? Just to give the intuition. So it's a formalism, a Gibbs-Boltzmann formalism. It's because this, in statistical mechanics, this form here, exponential minus the energy, is exactly the law which minimizes the mean energy plus the entropy. So if we consider for example, so the energy, so in fact, P lambda beta is exactly the probability which minimizes all over all the probability measure Q lambda, the mean energy plus entropy. So the mean energy is just over Q, so expectation under Q of this energy here. And the entropy is defined classically by the integral of f lambda logarithm of lambda, f lambda, with respect to p lambda, if there is a density, and if it was not, otherwise it's equal to plus infinity. So the entropy is defined classically. And so if you try to find which law minimizes this mean energy and the entropy, it's exactly this low p lambda. So it's why this form appears. So it's for the statistical mechanics point of view. And for the spatial statistic point of view, it's a nice model because it's an exponential model. Exponential model, exponential times a constant times a quantity. And so this exponential model has nice form for in statistic properties. So it was also extremely used in spatial statistics. For beta positive, this model was introduced by William Robinson for a model of gas. And spatial statistics with beta negative, the error process was introduced for modeling different objects. So just point out 2 points of view of this model. This model can be viewed first by a model of points with attraction or repulsion. It depends on beta. So there is a point, and you can keep in mind the point, and this area gives an attraction of a repulsion between the points. So it's a first point of view. It's a point of view around the points, but you can see also like a random shape. This is a shape, forget the point. A random set. It's a random set for which we add an energy, and the energy is directly depending on the area here. So 2 points of view. The point of view which involves the points and the attraction repulsion between the points, or the point of view of a random set with an interaction here. Okay. So now we have a nice model which is well studied in finite volume. Here's a variational principle and so on. And of course, we are interested by an infinite volume model. So just some information about why are we interested in the infinite volume model. It may be, but we want to build a stationary model with an infinite number of particles, for example, which model a macroscopic model with so infinity means when the number is large, and so in mathematics it's nice to modelize and the number of particles large by infinity. So it's nice to have an infinite number of particles to develop a macroscopic theory and quantity about that. It's nice to have a stationary model to use all the tools from the stationary theory, ergodic theory, and mean value, macroscopic, limit, and so on. So it's nice to have an infinite volume model. And in spatial statistics, it's nice also to have an infinite volume because we want to, for example, prove the consistency of the estimator. And so the estimator is built from a window. So we have a model, we fix a window, we make the estimation of the parameter, and we want to prove the consistency of this. And the consistency, what does it mean? It's when the observation window is large and becomes equal to, goes to RD, what happens for the estimator. And so we need an infinite volume model for which we look in a finite window, and the window is going to RT, and we prove the consistency, normality of the estimator, and so on. So for all these reasons we need, yes?
Today R is a constant.
Yes, today is a constant, yes. No random reduced for simplicity, but you can develop also this kind of model for, but it's by simplicity R is constant. Okay, so the question is, what about that? In which sense? And what is it here? And we will see after, is their limit is unique or not, phase transition result, and so we'll talk about that now. Okay. So in this setting, so this construction is quite important here, And tomorrow I will, in the second lecture, I will talk about a general theory for proving the convergence of finite volume Gibbs measure to infinite volume Gibbs measure. It's a new way to prove it, which is quite simpler than all tools existing. And but it will be the topic of the lecture for tomorrow. Today I will just to explain historically what we can use in this setting. And here a classical object is stochastic domination. Okay, so the proposition, what we can use in the following is consider beta bigger than beta prime and positive. So we can prove beta is that p lambda beta is smaller stochastically than p lambda beta prime, and it's smaller than the Poisson process. So let me just quickly recall the definition of that. For that we need a function f on the space on configuration is called increasing if f of a configuration is bigger or f on other configuration if mega prime you have the same in the same order. So it's finally f is just an increasing function. Here we have the order, the classical order, and here the order is in the inclusion between the points. Okay? And we say the definition. A measure P is smaller stochastically than Q if the integral of f is smaller than the integral of f dq for all increasing function. So it's a general definition of stochastic domination for probability here. And in this it's an analytic definition. It's not, for my opinion, so easy to feel what happened exactly in this domination here. I think the good interpretation of the domination is the inclusion of the process. What does it mean exactly? Maybe here. Interpretation. It's possible to have process n which follow p lambda, n beta prime which follow p lambda beta prime, and n beta which follow in distribution, so it's inequality in law. So it exists this on a common space omega with probability measure p, free point process, which such that the marginal are exactly S1, and such that, so for the moment it's easy, such that there is a strict inclusion. It means, so the smaller is beta, and beta is included in n beta prime, which is included in n. Okay, so it is an interpretation of the stochastic domination here. So it means this process is smaller than the Poisson point process. There are less points. So this, for example, is, you consider this one. So maybe I can, okay. This is n. And if you want to find n beta prime, it is included in n, and probably smaller. So you have the same point, but not all. Okay? And this one is included in this one, so such of points are these ones. Okay, so it is the representation of the stochastic domination by Strassen theorem, like that. So it's a good interpretation of the stochastic domination. It's smaller. So for example, the number of points here is strictly smaller than the number of points here. So we can control the explosion of number of points, for example. Okay?
Is it the only example or not?
Is
it the only example of domination or not?
For Gibbs process, you mean?
Yes.
I will talk about that. It's not so easy to have the domination for Gibbs point process. And I will give a general theorem to prove the stochastic domination. And it's really rare to have the stochastic domination. And I think for the Euler process, it's true, and it's quite a miracle. And it's the reason why this process is so nice, and we can develop so much result for this process. It's because the energy is such a way this domination is true. But in general, it's false. In general, for Gibbs point process, if you change the energy for a classical pair potential energy, it's false.
So I can find the domination. I can construct stochastic domination which is not the form of the.
This one?
Yeah.
No, it's equivalent.
It's
no, this is equivalent. That and that is equivalent.
Okay. Sorry.
So if you have that, it's clear. Now this it's true.
Yes,
and the other, it's true. It's the Strassen theorem, the representation of stochastic domination. So it was a question. Sorry, so I didn't. So it was a question. It's equivalent.
Okay, and formal questions. So I was late. So P, what is P? Is a measure on what? On configuration.
This one? This one?
No.
P is the Euler process. So I can keep P lambda here.
Yes, so
Okay? It's this process. It's the Poisson, here it's the Poisson point process on lambda, on the finite window lambda.
it's a density with respect to
And it's a density with respect to the Poisson process.
So this defines another probability measure on
Yes.
on space of configurations of points.
Yes.
Such that in every point there is a finite number.
Yes. It's the real process. So it's nice to ask questions, yet has to be clear. So it's a Poisson point process. And so we put a density here, which disturbs the configuration. And of course, imagine beta is positive. This density try to be maximum. So this density try to be maximum is this volume try to be minimal. So what is the difference between a Poisson point process and an Euler process? It's like a Poisson point process, but the spheres, the disk, try to minimize the volume. So there is a kind of an interaction between the disk because they try to overlap. Right? You can do a simulation about that, and it's clear. It's clustering process. The disk tries to overlap.
Yeah. in the definition of increasing, you maybe you. Okay.
It's okay.
Sorry.
It's just if omega, so it's other sense, no? You have to use the same stochastic. Yeah. Oh, sorry. It's okay. If you have a configuration bigger, this function is bigger, evaluated for a bigger configuration. And so, you know when you define this process, when beta is increasing here, it's not clear at all this kind of behavior. We can represent this process like a thinning of the Poisson point process. You consider the Poisson point process and you remove some points and you obtain. How to define the removing, it's not clear. We know it exists, but it's not explicit. So we have the Poisson point process. We remove some points by a kind of magical way, and we obtain the area process for beta positive. And if beta is increasing, we remove again new points and so on. So it's quite strange way to do it, but we can do it like this. Okay. Okay, now from that it's not too much complicated to prove the convergence of p lambda sum to something. Why? Because if I consider this event, so I fix just delta included in RD finite. The event, the number of points in delta is bigger than k. So fix k. Fix k. So this event is an increasing event in the sense that if you put f, the function f here, indicatrix of A, this function is increasing. Because if you add new point, if the configuration is bigger than this one, this event is more easily realizable. So this function, if this function is equal to 1, if you add new point, it's still equal to 1. So f is increasing. So apply now the definition here and the proposition here. We obtain that p lambda beta prime of A is smaller than p lambda beta of A, which is smaller than p lambda of A. Okay, so we obtain that. And so what does it mean? It means we are able to control the explosion of number of points. Because this quantity, for example, forget you don't know for the moment this one. What does it mean here? It means the probability to have more than k points in delta under the area process here, so for beta positive, it's smaller than the probability that the Poisson process has more than k points in delta. And so with that, it's clear that the number of points in A for the area process do not explode, because this quantity is dominated by this one, which we know this one. It's a Poisson point process, so it doesn't explosion here. Okay, so no explosion of the number of points in delta for p lambda beta, and you know it's uniformly in lambda, uniformly in lambda. Why? Because this quantity here is exactly the same that p delta. Because what happened in delta under the Poisson point process is independent with the outside of delta. So this quantity is here. So this quantity is independent of lambda, and here we control the number of points in delta uniformly in lambda. So here, no explosion of the number of points in delta for p lambda beta, and it's uniform in lambda. So I don't give all the details here, but that it's enough by compactness argument. It's a compactness argument here, so you control the explosion. It's enough to prove that p lambda beta converge to some p beta when lambda goes to Rd. For the topology L, I will give it in a moment, and it's a probability measure here. So the details of this stochastic domination, this convergence here, was done by Chais-Kotecky. So they are both. Kotecky in 1995. And what is this topology? It's just a convergence for the local topology. It means the probability of any local event converge to the probability of this event. Okay, it's for any local event. So the details about here, the compactness arguments and the stochastic domination of that is done exactly here.
Okay, and in more common terms, so this is a V convergence of probability measures on configuration of points. So V convergence with respect to some topology which you just mentioned.
Yes, and
is it?
But you can have also the convergence locally of the points if you want. You can find a family of process such that locally the points converge, almost surely. It's possible to have a representation like that. Okay, but in Lau you have the existence of an infinite volume process, which is a limit from that. Yeah.
Okay, I have a question. Okay, and the uniqueness of the Gibbs measure is implied somehow with this theorem, or?
We will discuss in a minute. Of course, this limit is not for a subsequence. It's a real limit for any sequence lambda which is going to Rd. Okay, so it seems to, so this limit it's a real limit. It's not for a subsequence. But here the boundary condition was fixed, more or less. We will discuss in a minute, in half an hour probably. The boundary condition is fixed. If we change the boundary condition, we will see exactly, we can obtain another limit here. And the phase transition occurs. But I will explain it in the second time of the lecture. It's a nice result in this topic, of course. Okay, for the existence of this process here. Okay. I would like just to, I think it's important to well understood this domination here. I can prove it. I can prove this domination if I give you a general theorem for that. So I propose to explain that now. I keep that. There is an important theorem of Györgyi and Kühnet about that, and so I will give you. So Consider two probability measure mu lambda is equal to f lambda p lambda. So it's a Poisson point process, a density, and the measure mu lambda. Okay? Consider another one, mu lambda. With two density. And the aim is to decide if mu lambda is dominated by nu lambda in a general way. For that we have to introduce, so we have an assumption, hereditary. Hereditary means, so the density may be equal to 0, it's possible, but not too widely. I explain. If f omega is equal to 0, it implies f omega union a new point is equal to 0. It's an assumption on f. It's exactly what we call hereditary, and that for any x and omega. So if you have a configuration f omega such that the function, the density, so it's f lambda, is equal to 0, if you add new points, the density has to be equal to 0. So it's what happens, for example, for the hardcore model. If you have a hardcore model, the density is equal to 0 when two spheres overlap, and see if you add new sphere, it's always a forbidden configuration. So it's basic assumption, hereditary, and thanks to the hereditary, we are able to define what we call Pampangelo density, or the local density of a point, is exactly what is the density of a point x in omega. It's exactly the modification of the density when you add a new point. And so, just to, yes, it's exactly this one. You add the point and you divide it by the density without the point x. And so to define that properly, you need this assumption, because if this one is equal to 0, this one has to be equal to 0, and we define what you want, 1, for example. It's not really important again. Okay, so it's Pampangelo density. It's the density, the modification of the density when we add a new point. And the theorem of György-Künet claims if, so just f x omega is smaller than, so f lambda, g lambda x omega prime. It's not for the same omega, for any x and any omega smaller than omega prime. Okay, if the Pampangelo density of f is smaller than the density, Pampangelo density of x in omega prime, for omega prime is bigger, we have more points. So it's unsure. I have a doubt. I think it's an equivalence, but I'm not sure. But maybe I will check and I will say it. But sure, this direction is true. So we have exactly nu lambda, which is stochastically dominated by nu lambda.
This theorem is it somewhat essential that all the measures on the functions have this subscript lambda?
It's what is important is you have a Poisson process here.
So you want
it doesn't depend
on a set of finite measures.
Yes, you need a finite subset lambda. It's finite. Lebesgue measure. You need a finite number of points, almost surely here, and it's a Poisson process. It's important. You use a absolutely here the Poissonian structure here. So with that, it's quite now easy to prove. Of course, this theorem is not so easy to prove, but you can check the proof in the paper. And it's not so complicated to prove the proposition about the area process, because if I consider mu lambda equal to p lambda beta, and now nu lambda is equal to p lambda beta prime. So what is exactly the density here? Papangelou density. It's when you add a new Boyd, what is the modification of the density? So what is interesting here, the normalization, the partition function disappeared because we divided the density. Here, so the normalization constant disappeared, and it remains only exponential minus beta, so Lebesgue measure of the ball in X with radius r, for which we remove the rest of the configuration L of omega. Yes. Okay, just a simple computation, compute the energy, the difference of the energy, and we obtain that. Yeah. And so for the second process, of course, it's the same thing with beta prime. Now it's a prime. Here it's important to have a prime here. It's not the same configuration. It's the main problem here. But for the area, all is fine. You will see. Okay, so, and now it's clear. Because if omega prime is, so omega is included in omega prime, so this set here is bigger. So this one is smaller, so this quantity here is bigger. And beta here, so just beta here is smaller than. I think I don't make mistake about the notation. It was beta bigger than beta prime. Okay. So this one is smaller than because it's including. So this one is bigger, and beta is bigger than beta prime. So this one here is bigger than this one, and so exponential minus this one is smaller than that. So it's a double. It's a double domination here. The domination because it's well done because omega prime is bigger than omega for that, and beta prime here. And so we obtain the domination here. And I think the miracle about the area process is exactly here, about this domination here. It's not true for, in general, for pairwise interaction and so on. Okay. Okay, now I would like to talk about the phase transition result. So it's related to your question. So p lambda beta goes to p beta. So we show that. So we have an infinite volume here, Gibbs measure area process for beta positive here. And this model was introduced by Widom and Rollinson for showing the phase transition result, a non-unicity of the Gibbs measure in continuous space. And so I will explain you what does it mean phase transition, and I will give you the main lines of the proof. And it's quite interesting and remarkable because it's more or less the unique example we have in continuous space of phase transition, where we are able to prove the non-uniqueness of the Gibbs measure and the instability of this convergence here. It seems clear there's convergence, but we'll see an instability of the convergence. And it's all is quite explicit and nice, and it's only one example we have. Okay, so now I will try to present you the very beautiful result of phase transition, and I will try to give the main lines of the proof. So what is first the problem? It's a problem of, for me, stability with respect to the outside configuration. So, what does it mean? So, put lambda included in RD. I define lambda plus exactly lambda plus the ball. So it's a Minkowski sum. It's clear what is it? It's just you have a lambda and you add the ball around here. Okay, so it's lambda plus here. And lambda minus lambda minus lambda minus the ball. So it's a set here. Line 1 and lambda plus. Okay. And now I define 3 different real process on finite volume. P lambda beta plus. It's exactly the same model. So finally, it's the same that I defined before, because lambda plus here, it's exactly here, so it's the same than before. But, so I just give an intersection with lambda plus. But I can define also with 3 boundary conditions, so it's the same here. Of course, the partition function it will be different, but I give the same name. You can imagine this model now. I consider only the energy view inside the window lambda. So I consider the union of balls here, and I intersect it with lambda, and I consider only that for the energy. And I can consider also the configuration minus. So if you want here, maybe it's nice to put a plus here. The F here is like 3. And here minus. Lambda minus, yeah. Only the energy which is inside here, this lambda minus. Okay, so what does it mean? It's okay?
What's the difference between PF and just P.
This one?
No. Between this and the original.
And this one. But this one, it's exactly this one. Because we consider the volume of the ball. Imagine you have a ball here. We consider the volume of this ball, not the restriction in lambda. Okay? So what is the difference in the physical point of view?
Okay, I missed the initial.
Okay, what is the difference? Here it's without particle on the boundary, because it's like the model is without particle here. Because we add this particle here and we consider all the energy of the configuration. This one, it's like, imagine your boundary at distance r is full of particles. So you put particle exactly at distance r, and it's full of particles. So when you add a new particle here inside, and you try to compute the energy of this new particle, what happens? This particle here, we add a particle here, and the energy is only the area of the ball inside lambda, because here there is particle places. Okay? And this one, beta minus, so represent this one. And now for the last one, in blue, it's like you put particle everywhere outside here. And so finally, it's like this one, it's full of particle. And when you add a new particle somewhere, only the part of the ball inside this square here contribute for the new energy. Okay, so the difference is very small. It's not really so important, because imagine your window is very large and the boundary is very small here. And so the difference of the energy may be very small in this free situation. And the question is it so small? Is it important, this difference of energy? What is the behavior of P lambda with respect to the outside configuration? What happened? So, and the phase transition will be exactly claimed here. So, like previously, we can prove the existence of the limit for the free models. Okay, it's the same, more or less the same problem. So we have P lambda beta. Now I called BC for boundary condition. So BC means plus, minus, or free. And it's just to write third the same thing. So I write BC for boundary condition here. So we can prove the existence of this limit for the local topology to a measure here. Okay, so an infinite limit like before by compactness argument and so on and so on. And of course, the question is this probability measure depends on BC? Is it different or not? Okay, and so there is a famous theorem. For Z equal to beta. So you have to choose the parameter of the energy, the inverse of the temperature, equal to Z. Z, I recall, maybe I don't give, but remember what is Z? Z is the intensity of the Poisson point process. Z is the intensity. So you fix Z equal to beta here. For Z equal to and Z large enough. So now you consider Z large enough. You really see how you can easily find a threshold for that. We can prove B, so it's a Z minus, it's different. So it's exactly what we call phase transition result, because these both measures are Gibbs measure. Gibbs measure in the sense of DLR equation, but it's a little bit different than I explained here, but it's obtained like this. So it's a Gibbs measure for the same model, and the two measures are different. So I would like to give you the main lines of this theorem. Okay. Do you know this theorem? Have you heard about that? So it's very nice result, and it's the only one way we have only one result we have phase transition for continuous model. So you see what it means. It means the boundary here condition when lambda goes to infinity to RD has an influence for the limit process. If you change the boundary at the infinity, it changes completely your model at the heart of the model. It changes completely the law of the model. So the boundary keeps an effect far away. It's the meaning of this phase transition result. Okay. So first, it's not to by QNet. By the theorem of Georgi-QNet about the stochastic domination. It's not difficult to see that P lambda beta plus is stochastically dominated by P lambda beta F, which is stochastically dominated by P lambda beta F. So it's an exercise if you want. It's just to write the density. We have the free density. They are here. You compute the Pampangil density, and you can obtain the domination that I explained. So you obtain that. And so finally, when you have the limit, you obtain this measure are stochastically dominated in the same sense. So we have this same domination. Okay, so we will concentrate to prove in the following that minus and F are different. So we will prove this one and this one are different, and since this one is smaller, it will be all different. Okay.
Is it obvious at this point that if P plus equals to P minus, then there is a unique Gibbs measure?
Yes, it's quite easy here.
Okay.
Because it's also a proof. It's like in a Ising model. It's a maximum phase and a minimal phase, and you can put all the other phase between these two phases like that. Exactly. So if this one has the same limit, all of these other one has the same limit. It's the same limit. So you can. This one is the maximum phase, minimum one. It's the same. All are the same. So it's not no phase transition occurs in this setting. But it's not so. No, it's not so difficult to prove it. It's just a stochastic domination, because all the other pairs have a density which is exactly in the middle, so you can prove.
Is there analogous theorem which shows phase transition in beta, but not in the boundary condition you use?
No, in general, in this case, the phase transition is only from the boundary condition. Of course, it's a bit complicated, but the real definition of a Gibbs measure is by the DLR equation. But I don't talk about that. But I will talk maybe tomorrow by the DLR equation and DLR equation, and we can prove that any Gibbs measure is a such limit for a fixed boundary condition. So finally, all the problem of the phase transition for Gibbs measure comes from the boundary condition. Okay, so a main point is the gray representation. Which is a kind of FK representation for twin Castellan representation by coloring the balls. So let me just present this gray representation. So we consider Q lambda a new model which is exactly equal to that what does it mean? So we consider a Poisson point process. L of omega is the union of pole, and NCC is the number of connected components. So we consider the number of connected components of L, and 2 to the power of this number is your density here. Of course, you need here a normalization constant like before. Okay. This quantity is clearly integrable because the number of connected components is smaller than the number of points. And 2 to the power number of points is integrable under the Poisson point process. So it's a simple formula to do. So it's clearly defined, and you can have that. So see this process like the Boolean model, the classical Boolean model, with a distortion with respect to the density 2 to the power number of connected components. Okay. Now we consider the thinning process. What does it mean? So I will explain with hands, it's easier. Consider a configuration, so in lambda. We consider, so it's easy, L of omega, it's the union of ball. Which admits a decomposition with respect to the connected component. So this, you can write it like a union for k is equal to 0 to the number of connected components of the connected component, which I call connected component k based on the point omega k. Maybe I can do a picture here. It's better than strong formula. So we have the point here. Okay, so we are here 1, 2, 3, 4, 5 connecting components. And we associated this connected component. So this one is CC1, and these 3 points is omega 1. Okay? And the same for the other. Is for example C2. We consider a numerotation, so on. It's a C2, and these 3 points are omega 2. Okay, so now we have a numerotation for the connected component and a numerotation for the points coming from this connected component. Okay. Now we consider a family xk of IID Bernoulli random variable with parameter and half. So we consider Bernoulli random variable independent each other and independent of the process will appear here after. And what we do for the thinning process, we keep each connecting component with probability on half, and we remove it with a probability on half. And we can do it thanks to that. So we consider here T of omega, the new process of point, is just the union for k equal to 0 to n cc L of omega of I keep the configuration omega k if xk is equal to 1, like that. Okay, so if capital Xk is equal to 1, I keep omega k. If it's equal to 0, I remove it. So, for example, I keep this one and I erase this one. I keep this one, I keep this one, I erase this one. Randomly, with respect to this quantity here. Okay? So it is a thinning process that we define here. So it is a gray representation claims the following thing. Okay. Okay, so let N be a point process with law Q lambda. So it's exactly, so first I consider a Poisson point process with this modification by this density. Now I consider this point process and I consider this thinning for this point process. Okay, so I consider this process, I make a thinning of each connected component, I remove with probability and half independently. And what I obtain here in distribution, exactly the same thing that the real process with parameter so z, beta is equal to z here, and the free condition with the free condition, and I just to add something, it's 2r. I change the radius, double radius. Or it was maybe simpler to consider the same here with an half radius. So, but never mind. There is a relation between, if you consider the radius r here you obtain 2r radius, and consider r an half of r and here r. Okay, so it is a gray representation. And it was given first in the paper of Chais and Koteki. Okay, so maybe I can...
The explanation for the name?
Sorry?
Do you have an explanation
for the gray? No. So I don't know exactly why they call that gray. So I will give, maybe it's important, the feeling how to prove that. So it's essential. It's a bit representation. So if I try to identify this law, I can test the process. So let f bounded measurable function. And we consider this quantity here, dp. The p here is just a probability space which contain this process n and the Bernoulli variables. Here we need a space with constant n. Okay, that we can write here like f expectation of integral of f t of omega q lambda d omega. Of course, we need to keep expectation here for the Bernoulli variables. And here, so we can use the law. Here it's here, so we keep the expectation. And f, I can try now to give the density of for z lambda, and f to the representation, I called it for k is equal to 0 NCC L of omega indicator xk is equal to 1 omega k, and 2 to the power NCC L of omega q p lambda d omega. And we have a big expectation here. Of course, by Fubini we can switch the integral and the expectation, but the expectation is just for the value of Bernoulli random variables here. Okay, so it's just the density which is developed here. And this expectation, we have number of connected components. So you can write explicitly the expectation for that. Is just finally a sum for all the value of this different quantity. So x1 is equal to plus 1 or 0, x2 is equal to 1 or 0, until the value x NCCL of omega equal to 1 or 0, and the function f union for k equal to 0 to NCC L of omega, and only for the xk which is equal to 1. The other I forgot. And p lambda d omega. And so it's at this stage that the density appears clearly what we choose this one. It's because when you consider the expectation here with respect to the Bernoulli, so we have to define the law of Bernoulli for NCC Bernoulli, and we have two choices, and so we have to divide, when you make the sum, we have to divide by the number of possibility, which is exactly 2 to the power NCC. And so the 1 over 2 to the power NCC disappeared with this 2 to the power NCC here. And we obtain exactly this equality here. Okay, and now here maybe, I don't want to give too much detail, but using the property of Poisson process, with the absence of memory, we can rewrite this integral like that. In fact, here, this absence of memory, here you have a part of the Poisson process which the mark is equal to 1 and which one is equal to 0 disappear. So finally, we have just, maybe I can give off more details, but we have just, here we can consider here a double integral with f of omega lambda for the first process. And for the mark with 0, we have another one, so there is no function for the other omega prime lambda for the other. And we have just the constraint that the Boolean model associated to omega lambda and the Boolean model associated to omega prime do not intersect. So with the indicator function L omega lambda intersection with L omega lambda prime is equal to the empty set. No intersection here. Okay, and from here so it's quite easy to compute this integral here with respect to that here. What is exactly the probability under P lambda such that the Boolean model of omega prime lambda do not intersect the Boolean model for omega lambda? It exactly, maybe I can make a picture. It is L omega lambda. If you want to solve this problem here, this constraint here, you have to force the point process omega prime lambda to have no point where exactly in this part we add R here. This constraint is solved if omega prime has no point in this area here, and the Poisson point process has no point in the area if with probability a Poisson point process has no point in this area with probability exactly exponential minus z times the volume of that lambda d L d omega plus the Minkowski sum with the ball B0R. And if you want, it's exactly f d omega lambda exponential minus that. The Lebesgue measure of L with 2R in place of R omega. So, and this density now is exactly the area process. Okay, so it's not so complicated calculus, but it's not so easy sometimes to follow. But what appears clearly here, it's this exclusion condition for this density here, which is the probability such that a Poisson process has no point in this area and is exactly exponential minus z times this area. And so it is here exactly the reason for which beta is equal to z, because the density here is exactly the probability under the Poisson process with intensity z. And so the density here is exponential minus z times the area. And so here beta is equal to z. Yes?
Could you comment again on the last line?
This one here? Okay. I decided to not give too much detail, but here you can see that like a kind of Poisson process, such that each connected component is marked by 1 or 0. And when we do that, it's like you give at each point 1 or 0 with mass delta 1 and mass delta 1 for 1 and for 0. And when we try to understand what is this process exactly, it's a kind of superposition of two processes. The processes, the Poisson point process with the mark 1 and the Poisson point process with the mark 0. And it's exactly what happened here. Of course, some details are missing. But here, we have the Poisson point process with the mark 1, and we forget the point process with the mark 0. So the mark 1 appears here. It's like here, it's the point process with the mark 1. And here, it's the point process with the mark 0. And of course, with the calculus, you obtain a constraint, which is the connected component with the mark 1 do not intersect the connected component with the mark 0.
So omega prime is roughly these components that are not included in this union.
Exactly. It's the rest of the configuration. It's the configuration with the mark 0. Mm-hmm. And this one is the configuration with the mark 1. It's exactly what happened. And but if you want, we can do the calculus in detail. Okay, but I think it's not at this stage too much important to understand very well the details here. What is important is to see we obtain this exclusion formula with a Poisson process, and so it appears here a density with exactly the form of the area density. Okay. Okay, so here we obtain exactly what we want. E lambda z, and it's the free. Oh, okay, something is missing here. I forgot the boundary condition. What is the boundary condition? We have to put the point inside lambda, because it's a Poisson point process in lambda. So here we have an intersection with lambda. An intersection with lambda. Because the points, it's exactly what, we have no points in this part here. Inside lambda, because we cannot have point here. So there is a lambda here. So it's what we obtain here, the free. And for 2r, the 2r comes from here. Okay, so the proposition is now proved. Okay. So it's a gray representation. Let me now give a gray representation for P lambda z minus. I don't want to give all the details like here, but it will be clear. How to change it? We don't want to put particle on the boundary here. So we consider now for the thinning process another thinning process. Remember, T and omega was exactly you have the connected component and you keep some connected component. Now we don't want to have connected component on the boundary, because it's equal to 0. So here, for t tilde n, so I just, so I didn't want to give too much detail, but so I start from omega, configuration omega. So I consider, like before, this connected component. And now we will keep the maybe I will give a picture because it's simpler. So we have the configuration of point, and we have the several connected components. And here we consider only the connected components which are inside the box. We forget the connected component which is the boundary of the box. It's possible if a point is just on the boundary and the ball crosses the boundary. We forgot all the connected components. So NCC tilde, it's exactly the number of connected components inside, strictly inside lambda. We forgot this one, and we will keep this in this process here. So what does it mean? So we consider this one, and I call this one omega boundary. So the configuration of the boundary, okay? And so this one will be, we can select it. We keep the connected component inside lambda with priority on half independently. Only the one which are inside. And we keep also the boundary on the configuration of the boundary. Okay, so the difference is in this setting, the configuration of the boundary is not random, we keep it. And inside, randomly, we decide to keep or to not to keep. Okay. Of course, now we cannot really use the same probability measure Q lambda because the random is only the randomness is only for the connected component inside lambda. So we have to define also Q lambda tilde like that. Okay. And so what we can do now, it's to consider, so this process is defined like t tilde omega. And so following the more or less the same calculus, we can prove So if n is a process following the law Q tilde, and the thinning of this process now in law is exactly an area process with probability with a parameter z minus n2r. So the difference here, so it's like the boundary, the influence of the boundary is given by the connected component which hits the boundary, and for which this component we keep it, and the other one we random by randomness, an half we keep or not. And you obtain that. Okay. So maybe now you can see what is the influence of the boundary. It's clear. The boundary, the influence of the boundary comes from, imagine lambda is large. The influence of the boundary comes from the size of the connected component which hits the boundary under the process Q lambda. Okay? Because if the process, for the process Q lambda, there is connected component inside, you keep it with probability n half, and the difference with respect minus n3 is that the connected component which hits the boundary is kept. Okay, so it gives exactly the difference for the two processes. Thanks to this gray representation, you can see what is exactly the influence of the boundary for the area process. It's clear? And so, so we can prove that if Z is large enough, Q lambda percolates. So, what does it mean? It means when lambda is large enough, when lambda is going to infinity, the density of the connected component which hits the boundary remains positive. It means the part of the particle, the density of the particle which hits the boundary by the connected component is strictly positive. So maybe it will be nice to give more detail. So it means if you consider, I can give a precise result. So expectation of the expectation of the cardinality of omega boundary. Omega boundary is a number, is a connected component which hits the boundary. Okay. If I consider this configuration, the number of points is the configuration which hits the boundary. So under Q lambda, and I divide it by lambda, by the volume of lambda. Okay, so this quantity is the density of the particle of the bond connected component which hits the boundary. This quantity converge to something which we call, for example, density rho, which is strictly positive. So that, I can also give a proof of that. It's not too much complicated. We can prove that this process dominates a Poisson process for Z smaller. And so we can, for Z large enough, this process dominates a Poisson point process which percolates. And so finally this one percolates also. By stochastic domination we can obtain that. Okay. So maybe you can see appear now all the piece of the puzzle for the phase transition result, because if we consider the density so if I consider now the intensity of point, the intensity of point defined more or less like that. The intensity of point for P P minus PZ 3 and so 2R. So this quantity is the density of point of this phase here for the 3, for the minus, it's simple like this, it's bigger, minus the density of points of this phase here. Oh, sorry. Yes. So here is the density of points for this phase here. Here's the density for the phase with free boundary condition. What is the difference? If we consider the both gray representation, the difference of the gray representation for minus and for free, it comes from exactly the points which are on the boundary, for which the connected component is the boundary. And this density here for Z large enough is strictly positive. And so the difference of the density for this phase and this phase is exactly equal to Z.
Sorry, and by percolates here we mean exactly this property.
For example, yes. Yes, we can say that, yes. We can see also by an infinite volume process, we can prove this process admits an infinite volume limit, which percolates means existence of infinite cluster, but we can use this property yes, for finite Euler. And so this density rho is exactly the density of the connected component which is the boundary, which is exactly the density, the difference of the density of the process minus and free, which we recover this density. So these two processes don't have the same intensity, and so they are different.
So how can we relate this definition with what you gave 2 days ago when we were looking at slightly different model, but we were finding trying to calculation was existence of a infinite cluster.
Mm-hmm.
And here instead of this you impose something which is more, which is strong, which seems to be much stronger.
The best way is to define when you have an infinite volume model. Mm-hmm. But sometimes it's not necessary to define it to use the property. So we don't need to define an infinite volume model for Q lambda for proving what we are interested in. We are interested in not by the process Q lambda, but by P lambda here. So P lambda here, if you want it's a kind of another definition of percolation. Yeah.
Yeah, but probably my question was if the intuition came from you first, talk is useful or useless in understanding of this relation?
Yes, but it depends what you want to do. Here, I think this point of view is enough. But in the other talk 2 days ago, we were directly interested by the topology of the infinite volume model. It depends what you want to do.
Okay.
It depends what. Because here I give an application of the percolation. It's directly related to the percolation of the Poisson point process here. Because you can prove you can prove that Q lambda dominates the Poisson point process for a parameter z. So here it's for z, and here it's for another z. I think it's a constant. It's a constant alpha z. So we can prove this kind of thing. Okay. And with alpha strictly positive. So for z large enough, so this model here, P percolates, we saw that 2 days ago, percolates for z large enough. So for alpha z large enough. But alpha z large enough means exactly z large enough. Okay? And this one is bigger than this one. So this one has an infinite volume cluster with positive density. And since this one dominates this one, it's clear that the density of this point which is the boundary is bigger than the density of this infinite cluster here. It's clear? Okay. So for example, for proving that, it's better to have a definition of infinite volume cluster here for the Poisson point process here.
And this property holds for the Poisson.
And for the Poisson, this one is true also, but for the Poisson you have a stronger one, which is the existence of an infinite cluster, connected cluster, an infinite connected component. That's clear?
But you don't know how sparse it is.
No, it's quite easy to prove. It's quite easy to prove because the density is positive by stationarity. You don't need to know how it's. You have clearly that the density is clearly positive because by stationarity you prove this density here, the density of the cluster, is exactly the probability such that 0 is inside the infinite cluster. Is up here belongs to the unbounded cluster. It's clear? So this probability is strictly positive, and so it's exactly the density of your infinite cluster by stationarity. Okay, maybe it's clear. It's clearer now. So we can do like that and obtain by this result. It's quite easy. It's also an exercise if you want by Georgi-Künet. So by Georgi-Künet, Q lambda z dominates the Poisson point process with an infinite cluster. So we obtain this kind of property here. And it's exactly the gap between the two phases here, the density of the between the two phases.
I'm sorry, maybe I missed this. Could you please clarify once again why is it equal to z? The top of it.
That? Okay. Maybe I was not very clear here. So what is the difference between this phase and this phase? We saw we have the process Q lambda, which define a point with a density 2 to the power the number of connected components. When we have that, what we are doing? For this phase here, each connected component is kept with probability on alpha. And for this phase here, we do the same, except it that the phase which the connected component which hits the boundary is kept and not delayed with Frobenian half. So of course the density of this one is bigger, and is maybe it's Z/2. Doesn't change. Oh, it's not whole. It's rho.
Oh yeah, now it's fine. Okay,
It was a question.
Yeah.
It was. Sorry. Sorry.
Just wanted to-
Sorry. No, it's rho. It's too big, we said. Of course. It's just this quantity. Thank you. No, I was maybe I was a little bit not really organized at the end to put all the puzzles together. But is it clear for? Or do you have question about the organization of this phase transition? So of course the proof of the phase transition is quite it's quite long and technical if you want to write all the details. But I think the main ideas are here is to I can give summarize you construct two gray representation for two different phases with different boundary condition, and this gray representation don't have the same density, because one keeps the point of the connected component which hits the boundary, and this connected component has a non-negligible density if the process Q lambda percolates. It's more or less what you can say here. And so what a key point is clearly the gray representation, which we have only in this for this special Hamiltonian, for this special energy. Yeah. Okay, so it's an historical result, important result, statistical mechanism for continuous model. And so it was the topic of the day. Tomorrow I would like to talk about how to prove existence of Gibbs measure, not only for this energy, but for general energy. How to produce an infinite volume model. The proof will be precise and based on new tools related to specific entropy, which I developed recently, and with my co-authors. And so it will be the topic of tomorrow. We start from zero about the Gibbs process, the energy, and I will present you a general theorem to prove existence of Gibbs measure.
Just a more general question, more or less general question. Can you show again this blackboard with the theorem?
The one that is
Yeah.
Which one?
The blackboard which is behind this.
Yeah. Oh, okay. I forgot.
Okay.
Oops.
Not
This one.
Okay, sorry. It's right. Do you know?
Maybe.
Actually, do you know that? First, is it true or is it believed to be true that Z is a critical parameter? Is the critical value of beta? Is it true or not? It's for the result for small beta and so on.
I think no, it's not the critical. Probably it's not the one. It's just one point which is critical, but we don't know if there is also one.
Do you know that there are points below criticality? So is it obvious that the critical regime is
No,
not?
I think it's not.
So otherwise
I
you can
think
say
it's
it
not-
is position, right?
Yes, I think we don't. I think there is a different point of view. It's not. Okay, here we have what I have in mind. What I'm doubted. Here we have a mind with only one type of particle. In general, where you have a multi-type particle system, for example, with two types, red and red and blue particles and in competition, so on. Maybe the phase transition, the non-uniqueness of the Gibbs measure is for a large range of parameters. And so when you have only one type of parameter, maybe I think we have only one value for which the phase transition occurs. And maybe it's what happens here. Maybe it's only only one value for which the phase transition occurs. It's different, like for particle with two types, for example, even for Ising model or something like this with two types particle. Here it's only one type of particles, and maybe the phase transition is only for one value, the non-uniqueness of Gibbs measure. But it's not. It's my opinion, but I'm not sure it is shared by everybody. And in any case, it's difficult to prove. And because what you have in mind about this fact?
Yeah.
What do you think about that? You do have
I just thought that it's about image somehow like an Ising model when it has some small beta is two regime and large beta is one regime. So I think it seems to be that, for instance, for beta equal to plus infinity, there are. Can you consider this model?
For plus infinity.
There should be a lot of.
But what is strange here when z and beta, when z goes to infinity, it's a very strange thing here. When z goes to infinity, so with beta, because beta is equal to z, what happened here? If you consider the process Q lambda is very dense. It's because Q lambda is just the process, is a Poisson process with the density to the power number of connected components. So this process becomes really dense. So more or less, it covers the space when z goes to infinity. So what happens? The density of the cluster, of the infinite cluster, more or less is equal to the density of the process. All the points, more or less, all the points are in the unbounded connected component. And so what is the difference here? This phase is completely full of the point of Q lambda, and this phase is empty, more or less, because here, what are the connected components, which is with an alpha the other one, but for the rest of the phase of the connected component, this part is more or less empty. So we have a kind of gap. All the points are here from Q lambda, and this phase is more or less empty. So it's quite strange with this kind of competition between the empty set, empty configuration, and the full configuration. So when z and beta is large, we obtain asymptotically a first Gibbs measure which is full, the space is full for the density covered by balls, and another phase which is empty. So it's quite strange extreme setting. Yes. It's true.
Maybe at this point we should thank the speaker for the lecture and for answering the oversized amount of questions.
That's okay.